Hey guys, good morning for me, good afternoon, presumably by the time you watch it. We are finishing up or starting up day two of the next chapter, chapter three. I thought I'd also just finish up a couple of these things that we didn't do. Um, so just a slightly different way of writing a line here. We've got x over a plus y over b equals 1. You know that sometimes it's hard to see on the YouTube, so I'll zoom in a lot there. What is the x-intercept? The x-intercept is where you intersect the x-axis, where you have a height of 0, so y is 0, so I'm kind of using that finger method, although it's more like a pen method right now, and saying that x over a equals 1. Oh, so x would have to equal a. In a similar move, I can see that y over b equals 1 if x equals 0. So my y-intercept should be b. Perhaps now you can understand why it's called, well, this is called intercept form. Down here, we just had some more examples we didn't quite get to. If I subtract 6x from both sides, I get y equals negative 6x minus 3. That has a b value, a y-intercept of negative 3, and a slope of negative 6. So instead of going 6 down, I'm going to go backwards and 6 up, relatively steep downhill bit there. Similarly, here I'm going to get a negative y equals negative 5x, and then y equals 5x. This is an, oh, geez, you can't see what I'm doing. Sorry about that. This is an example of direct variation, which we'll deal with more later. Goes through the point 0, 0, as all direct variation does. It goes through 1, 5, and 2, 10. These are just so easy to put in that it will help me in drawing that line. Although technically, in order to get a line, I only need 2 points. A little bit of an awkward angle to be drawing there, and I'll blame it for having me miss that point. Okay, on to the new material where we deal with systems of linear equations. A system is more than one equation, which can often be solved simultaneously. Solve this system of linear equations by graphing. This is a method which I think is only useful for finding the region in which a solution might be, not for finding the actual solution. You've got to be a little bit too precise, especially if the answer comes out to be like a 2.27, 1.49. You're not really going to be able to see that on a graph, but you'll see, oh, okay, well, that's in quadrant 1. Just to remind us, the quadrants go 1, 2, 3, and 4 counterclockwise around, starting with the x-axis. Okay, so 3x plus 2y equals 12 is in standard form. I'll use that finger method. If x equals 0, y equals 6. If y equals 0, then x equals 4. And I will draw a reasonable line which goes through this. Negative x plus 4y equals 10. If x equals 0, y unfortunately equals 2.5. There you are at 2.5. And if y equals 0, then x equals negative 10, and we get something which looks like this. Okay. So again, my solution is somewhere in here. Admittedly, if I had done it with a ruler, it would come out a little bit on the nicer side, knowing that presumably they meant us to get an actual integer answer here. It's probably 2, 4. Let's just see. If I plug in a 2 and a 4, we get a 6 and a, now maybe 2, 3, 2, 3. That seems like it will work. And it seems like it would work there. Okay. So again, good enough if you know that the answer you're looking for is a series of integers, but not very effective otherwise. When we get into nonlinear systems, graphing will be a good way of finding what the nature of solutions might be and what regions they, plural, might fall into. But as for right now, it's not a preferred method. Here are the two preferred methods. Substitution usually goes by substitution. Sometimes I feel like we could call it transitive. If you guys have studied a little bit of the same theorems we learn in geometry, that would make some sense, but everyone calls it substitution as far as I know. Now, substitution is where you typically solve one equation for one variable, but you don't really have to. You can be a little sneaky from time to time. So the traditional way over here would be to say y equals 2x plus 1 is just rewriting that first equation and then jamming this value of y in over here. So I'm going to write 4x plus 6 what? Oh, instead of y, I'm going to write 2x plus 1, the parentheses really help, equals 26. And I could easily solve this equation for x. However, I've got another version of this, which is still substitution. If you can think of that first equation as 2 of 2x plus 6y equals 26, and maybe you don't even have to write it, but you can think of it that way, and then realize, oh, wait a second, I already have an expression for 2x. Didn't solve for x, but maybe it was a little sneakier here. 2 times that expression for 2x is y minus 1 plus 6y equals 26. And I can solve this one. All right, 2y minus 2 plus, don't know why I wrote an equals, 6y equals 26. Adding 2 to both sides, I'll end up with a 28 over here. Gathering my like terms, I'll end up with 8y. Hope I did this one right. Because y should equal 28 eighths, also known as 14 fourths, also known as 7 halves. Okay, that's not an unusual one. Regardless of whether you do elimination or substitution, once you find one variable, chances are you're going to substitute back in to find that other one. So plugging in this 3.5, that's 7 halves, minus 1 should be, so I'll write it out, 7 halves minus 1 equals 2x. So we get 5 halves equals 2x, and x apparently equals 5 fourths. Those are my two answers. If they are, yes, y equals 7 halves. If they are x and y, you are welcome to write them as an ordered pair. If there are any other variables, including a and b, you can't. Just for the fun of it, I'm going to go back over here. 4x plus 12x plus 6 equals 26. I'll get a 16x equals 20. I will get x equals 20 over 16. They're both divisible by 4. I'll get 5 over 4. And we got the same answer. So looks like you did it well. Nice. As opposed to substitution, elimination goes by several different names. Sometimes you will hear it called elimination. Sometimes you will hear it called scalar multiples or linear combinations or anything of that nature. Sometimes the addition subtraction method. And here, even at Harvard Westlake, the 7th grade teachers tend to, even though sometimes it's called the addition subtraction method, really prefer that subtraction bit. I have no such worries or concerns. So the way I would presumably do this is by multiplying the bottom one by 2, the bottom equation. So I have 4x minus y still equals my favorite number, 17. And when I multiply the bottom one by 2, and sometimes I'll write a little 2 here to show what I'm doing, I get a 4x plus 6y equals 19 times 2 is the same as 20 times 2 minus 2, so 38. And I am in good shape because I have the same or additively opposite coefficients in the same place. So that 4x and that 4x. I know that in 7th grade, a lot of times they teach you to multiply by a -2. So I have a 4x and a -4x so that I can add those two equations to eliminate that variable. But we're big boys and girls and we can subtract. So I will do that. 4x minus 4x is 0x. I don't even bother to write it. It was the whole point of this exercise. -y minus a 6y is -7y, and 17 minus 38 looks like it would be a -21 to me. And that is looking pretty promising. When I divide by -7, I get that y equals 3. As I mentioned, even if you are using elimination, chances are you are going to substitute back in to any equation. I could do the one where I multiplied the bottom equation by 2. I could do the original one. I could do this original one to figure out what it is. This one looks easiest to me. I'm going to say 4x minus, instead of y, I now know it's 3 equals 17. Again, this is looking pretty promising because when I add 3 to both sides, I get something divisible by 4, and x apparently equals 5. So again, x and y, you can either box both of those answers, or I could write it as the ordered pair, x comma y, and box that one instead. Up to you. People might have noticed that instead of multiplying the bottom equation by 2 and eliminating x, maybe I multiply the top equation by 3 to help eliminate y early on in the game. And that would be perfectly fine as well. In that case, you get to add instead of subtract. Yay. All right, use elimination method to solve this system. Let's see if I can get this on the screen. Hint, do not substitute first value that you find back into the system. Instead, start from the beginning and eliminate the other variable. It just read that and it didn't went in one ear, out the other, as sometimes happens. Let's see that again. Use elimination method. So this is where we are going to get the same coefficient in front of the same variable. Hint, do not substitute first value that you find back in the system and eliminate the other variable. Okay, so they want us to use elimination twice. I suppose we can. I don't know that it's necessary for you guys to sit here and watch me do this. Feel free to give this a little fast forward. Sometimes I'll just pause it and do it and see if we ended up in the same place. I'm multiplying this guy by 2. 3x plus 4y equals 7. I have a 10x minus 4y equals 18. Adding, I get 13x equals, looks like 25. And x equals 25 13ths. Okay. Yes, admittedly, plugging that back in does seem like a bad idea. So instead, I'm going to multiply the top equation by 5. I'll end up with 15x plus 20y equals 35. And the bottom equation by 3. Notice I multiplied this one by that coefficient and this one by that coefficient, guaranteeing that I will have the same coefficient in front of both of them. 3, so negative 6y, and multiply by 3, so I have 7. That's always guaranteed to work, but it is not guaranteed that it will be the quickest route. If I were programming a computer to do this, that is exactly what I would do. Multiply the equation 1's by the second equation's lead coefficient and equation 2 by the first equation's lead coefficient. No thinking required, but it might be a little harder. All right, I'm subtracting. So remember, when I subtract a negative, I end up adding. Get 26y equals, and I'm subtracting here. So that does look like another 7, and y apparently equals 7 over 26. Not very friendly answers. Very glad I wasn't supposed to look for those through graphing. Another way of asking the same type of question, find the point where these guys intersect. So we are really just solving this system. I see a 4y if I multiply that by 3, and a 6y if I multiply that by 2, we'll end up in that same place with a 12, or in fact a negative 12 in one case y. So welcome to do that one. I don't think it brings anything new to the table. Miss Benton wants to sell 40 pounds of mixed nuts for $3 per pound. She has cashews selling for $3.50 per pound and peanuts selling for $1.50 per pound. How many pounds of each type of nut should she use in the mixture? So this is where I'm going to do a let statement. Mixed nuts and cashews. I don't know. I'll go for X and Y. Let X equal your pounds. Not a hashtag, but a pounds. Of mixed nuts. And Y equal my pounds of cashews. So I know that all together, I'm going to end up with 40 pounds of this stuff. The mixed nuts cost $3. So if I take $3 and I multiply it by my number of mixed nuts, it tells me the price of those. She has cashews for selling $3.50. I could put an extra 0 in there, but it doesn't really change anything. What did I just? Totally missed that one. All right, reading it wrong. Sorry. She has cashews selling for $3.50 per pound. So that is that 3.5. Why? I'm missing something. And peanuts selling for, okay. This was supposed to be peanuts. I got it. I got it. Sorry. Sorry, trying to think too fast. So we've got this 1.5x plus 3.5 y, and that's the cost of this, that's the cost of this, should equal the cost of this, which is 40 pounds times $3 per pound. There we go. Now we're cooking. Okay, so here I have another system of equations. Admittedly, I've got these decimals. If I multiply this whole equation by 2, I don't have to deal with decimals anymore. If I multiply this whole equation by 2, I'll end up with 3 x's, so maybe at the same time. Oh, my cat scared me. I'll multiply the top equation by 3. Yeah, I get it. And we can start doing elimination there. So I'm going to squeeze it into this corner. Sorry, it's a little disorganized this time around. 3x plus 3y equals 120. I've got a 3x, as we decided, multiplied by 2, so plus 7y equals 40 times 3 times 2, so we've got that 240. I'm going to subtract, but I'm going to do it a slight bit different. I'm going to subtract the top one from the bottom one. So 7y minus 3y is 4y, and I get 120. It looks like y equals 30. Plugging back in here, I get x equals 10. So I guess we have 10 pounds of peanuts. I'll use LBS instead of the pounds thing. Peanuts. And 30 pounds of cashews. And that looks like a good answer to me. Hey, sorry about misreading it. These things happen. Okay, I think that is actually where we are going to end it. Sometimes we talk about these different language for describing these things. If linear systems do not intersect at all, they're considered inconsistent. Both equations can't happen at once. That is inconsistent. Another way of describing that, of course, is that the lines are parallel, which as a geometry teacher, that is how I spell parallel. If they are consistent, they could be one of two things. They could be independent or dependent. Independent, as the name implies, one thing can do one thing and the other will do the other. But dependent really means that it's the same equation twice. In this case, there are infinitely many solutions. In this case, there's one solution. Well, if there's infinitely many solutions, it doesn't mean that everything is a solution. What we really have to do is write an equation for one of these lines, since they're both the same thing, and say that that is my answer. So they wrote it in formal set notation here. This reads x and y such that ax plus by equals c, where they fill in like 3 and 2 and 12 for a, b, and c. And that's a perfectly good way of writing it. I would just presumably leave out the formal set bit of it and just say that here's my solution. Okay. 2x plus 3y equals 12, or whatever the equation happens. All right, guys, have a good flex day tomorrow. We'll catch up with you soon. Thanks for putting up with the video. I know it's just going to be stupid hot in here this afternoon. Actually, looking at my Alexa right now, it only says it's going to be 93. That's not so bad. Better than it was predicted. Okay, have a good one. Bye.